In this video, we're going to be looking at how to do operations with numbers that are in scientific notation. The definition of scientific notation, again, is a way of expressing very large and very small numbers as a product greater than or equal to 1 and less than 10 times 10 to some power. And this is the generic format, the number n times 10 to some number p. And there's two methods to doing this. The first method that I'm going to talk to you about is simply to convert the number from scientific notation back into a regular number. We have 3.63 times 10 to the fifth. That's going to be 363 and 5 decimal places. So that's going to be 1, 2, 3, 4, 5. And that's being added to 7.28 times 10 to the third, or 728, 1, 2, 3. And to do addition, we'll just go ahead and stack them vertically. 0, 8, 2, 0, 7, 3. It's 370,280. But since we started in scientific notation, we should end in scientific notation. So we're going to go 1, 2, 3, 4, 5 to the left. That's going to be 3.7028 times 10 to the fifth. And that's one method to do it. And I'll be honest with you, that's not my favorite method because we had to convert twice. We had to convert from scientific notation into the actual numbers. And then once we got our answer, we had to go back again to scientific notation. So let's go to method 2, which is how we're going to spend most of our time. And I want you to think about scientific notation very similarly to how you think about fractions. Because a lot of the rules between fractions and adding them together are the same as the rule for adding numbers in scientific notation. What do you need to add two fractions together? You need a common denominator. The denominators are not the same. You're not able to add the fractions. What do you think we need to make sure is common or the same in our two numbers here in order to add them in scientific notation? That's right. The power of 10 has to be the same. Here it's a 5. Here it's a 3. It doesn't matter which one you make it. You just need to change one of them to match the other. Let's go ahead and change the second one to match the first one. So what we're going to make this is to the fifth. So we're going to move 2 more places, making it 0.0728 times 10 to the fifth. And that's being added to 3.63 times 10 to the fifth. Well, stack it vertically, keeping in mind that when you add decimals, you want to make sure that the decimal points are right on top of each other. Bring those down because they don't do anything with anything. $3.7028, which is exactly what we got last time after we did the conversion. And it is still 10 to the fifth power. We don't need to do anything else. Pretty simple, isn't it? Well, that's the rule for addition. So let's take a look at multiplication. Now those same two methods that we talked about can be used here as well. We can do 2 times 10 to the fifth, which would be 2 followed by 5 zeros. And we can do 3 times 10 to the third, which would be the number 3 followed by 3 zeros, and multiply those together. But look how huge those are. Do you think that's really going to be the most effective use of our time? I don't. So remember that multiplication, which is all that we're doing right here, can have both the commutative, which allows us to move the numbers around, and associative properties applied to them. So if I move the 2 and the 3 next to each other, that's pretty easy to do. Times, and let me move the powers of 10 next to each other. Well, what's 2 times 3? 2 times 3 is 6. Times 10 to the, and this is a time when you can remember your rules for exponents. What do you do if the base is the same? We're multiplying them together. What do you do to the exponents? You add them. 5 plus 3 is 8. So it's 6 times 10 to the 8th. A lot easier than having to multiply off and carry all those zeros and everything like that. And the same thing can be done with division as well. Remember, division and multiplication are essentially the same thing. The latest trick that I like to use about it is anything that's on top, as long as you keep it on top, you're good to go. And anything that's on the bottom, as long as you keep it on the bottom, you're going to be good to go. So a nice way to split this up using both associative and commutative property, because remember, everything here is really multiplication and division, but you'll see how we deal with that in a second. We can do 8 divided by 2 times 10 to the 7th divided by 10 to the 5th. Now I want you to be very, very careful. Notice that the operations here are multiplication. You don't need to be doing this if that was addition, but everything here is multiplication on top in the numerator of the fraction, and it's all multiplication in the denominator of the fraction as well. Okay? You want to remember that. Well, 8 divided by 2 is 4. And 10 to the 7th divided by 10 to the 5th, 7 minus 5 is 2. 4 times 10 squared. Pretty simple, isn't it? I thought so. So let's actually use this in a real problem. I'm showing that the area of Texas is about 2.69 times 10 to the 5th square miles. The population of Texas is about 2.61 times 10 to the 6th people. What is the average number of people per square mile in Texas? Well, we're doing people per square mile. So we'll put people on top. 2.61 times 10 to the 6th over miles. 2.69 times 10 to the 5th. And doing exactly what we just did on the last problem, we can split it up. Let's do 2.61 divided by 2.69, which is going to be approximately, and I'll just keep the number of spaces the same, 0.9703. I'll say that's approximately what it is. Times 10, and we have 10 to the 6th divided by 10 to the 5th, 6 minus 5, is 1. Okay, so we have 0.9703 times 10 to the first. This is neither being written right now in scientific notation, nor is it in a regular number notation. It looks like scientific notation, but what's wrong with it? That number is not between 1 and 10. So we'd have to move the decimal point, or we can just, well, leave it alone. In fact, if we move the decimal point 1 space, you're going to get 9.703 is the actual number, which in and of itself is between 1 and 10. So that's really our answer. It's 9.703 people per square mile in the state of Texas. And that is how we do operations using scientific notation.